Hey, what's going on, folks? It's Mike here, and welcome to today's talk, which is going to be an introduction to computational geometry. Now, this is a little bit outside of the norm of the lesson-by-lesson things that we do, but I recently gave this lecture at a math club at my university, and I thought it would be worth sharing to the greater public here so that you could have a sort of lightweight introduction to computational geometry. So this might be useful to just sort of get you interested in geometry. After all, if you're watching this channel because of the graphic series with OpenGL, for instance, I think this might be interesting just for you to know or see some resources. So again, here's a high-level talk on an introduction to computational geometry. I hope you enjoy it. And with that said, let's go ahead and dive in here. So for today's lesson here, I've actually got slides prepared. So we're going to go ahead and walk through these, and you can find the sort of introduction to computational geometry. And of course, you know about these other things here, like the courses. And of course, you're watching this on YouTube, so you know about my channel. But here's the talk anyways, and let's go ahead and dive into it. So you'll go ahead and see this is just going to be a high-level introduction to the various things that might be interesting here. Here's sort of an abstract if you want to decide if this is worth your time to commit the next 40 or 50 minutes to. But here's the sort of goal, though, just to give you a high-level survey of computational geometry, some interesting problems to solve. This is by no means comprehensive, but again, I think it'll be interesting for you to think about here. All right, so with that said, let's go ahead and talk about some geometry, things like this, and what it means here. And a place where you can start to think about computational geometry is actually from the Wikipedia page here. So feel free to go ahead and explore the page here, and I think it gives a pretty good high-level definition here. I'm just going to zoom in a little bit here so you can see that, well, it's the branch of computer science that has to deal with studying algorithms in terms of geometry. So I hope this wouldn't come up as too surprising. And a lot of the things that we have to deal with in geometry are, well, algorithms, computational complexity. So if you're familiar with big O notation and these types of things here, we're often trying to find upper bounds, average case, or even lower bounds in some instances. And if I kind of scroll through this, right, a lot of the algorithms and things that are studied in computational geometry are directly applicable to computer graphics, computer-aided design and modeling, but many other things, as is going to be listed here. And I'll go ahead and flip back to the slides here so you can see yourself here. Now, where are the origins of computational geometry? Or let's say you're already tired of this video and you just want to go ahead and read something concrete and, not have to watch a video. You can go to Michael Ian Seamus's thesis here and find what you would find in a lot of computational geometry courses, the sort of topics on complexity, convex hulls, which we're going to talk about a little bit in an applied scenario, intersection tests, inclusion, closest point, these types of problems here that are kind of laid out things in a nice guide. So this is often what people will reference. But, talking about computational geometry, we've had geometry since, well, I don't know, thousands of years. So if you're approaching this problem as a mathematician, you're actually going to say this is relatively new stuff to look at somebody's thesis from 1978. So there have been other foundations to what we now apply in computational geometry by George Voronoi here. These Voronoi diagrams here since the 1900s, and many other earlier works going back to, origins of mathematics where we're applying geometry and trigonometry. So those are things that are directly applicable here. So we'll just kind of keep that in mind here, that, computational geometry using computation has been, this field has sort of been coined around the 70s or so. All right, now again, where is computational geometry used? Well, I listed a few of the obvious candidates here: computer graphics, CAD, if you've done 3D modeling, these sorts of things in either like SolidWorks or maybe Blender or these types of programs. But oftentimes in robotics, for instance, for motion planning, finding things like shortest routes that might be obscured by objects, and navigation systems is a major use case of computational geometry. And of course, there's many, many other fields here, such as molecular modeling. So thinking about folding and these types of applications, integrated circuit design. How do I lay out the actual digital components on a motherboard or some sort of chip here are all problems where we're sort of trying to figure out, where do we pack things and, and sort of orient things so that they work here. Even things like database search and, some of the insights from, again, how we route information and store information. These are all topics where computational geometry or the knowledge that's sort of grouped into this field or maybe a course that you would take would be useful. Now for today though, we are going to focus on games graphics. This is sort of the domain that I understand. So specifically, we're also going to be looking at collision detection. That's the problem that I want to visit today to give you this introduction. All right, so with that said, we're going to look at things in the context of a physics engine, because one of the fundamental problems is deciding or understanding in computational geometry, when do we have a collision between two 3D objects? So here's sort of a nice example here. This is from the Bullet physics engine here, showing some collisions here in this, what looks like a Jenga tower, but it's actually just a bunch of scaffolding here, a bunch of pallets. It looks like wooden pallets. But really, when we're modeling this physics system, the common way to build an actual physics engine that you'd use maybe in a game or a simulation or maybe a movie in some sort of environment is to have these three sort of components. So I want to go ahead and give you an overview of what those look like. So the first of that is this idea of integration. And this is sort of your physics 1 class where you're, figuring out how do things move, the kinematics, right? Modeling some forces, thinking about kinetic energy, potential energy, these types of things here, the velocity and the acceleration of objects, as you can tell from this diagram here. And the next part, again, of our physics engine is detection. This is what we're going to focus on, so we'll revisit this slide in a moment here. But how do I know that this spherical object is colliding with this other spherical object? Well, it happens to be that spheres or circular collision, in this case, in 2 dimensions, is quite nice to work with. So we'll revisit this in a moment. And then finally, resolution. Okay, so what happens with the actual collision? What's the actual response that we get when two objects collide into each other? So usually we might use something like the direction or the velocity which this object is moving and sort of modeling that as a vector. And then we have our other mathematical tools. If you've done a little bit of linear algebra to figure out, hey, what's the sort of normal, or where would we apply some force? And so we have some tools there. But let's go ahead and focus a little bit more on this collision part of the physics engine here. So the problem that I'm going to set us up for the remainder of this talk here, this lecture, is, how do I detect if another object collides with this bunny here? So I'm going to try to have two bunnies collide here. And, this particular bunny, which is famously known as the Stanford bunny, you can go ahead and click on that, a laser scan bunny at Stanford. It's made up of triangles, which I'll show you, about 69,451, I believe the official bunny is made up of. But let's go ahead and think about this. How do I detect collision with objects with this bunny here? So here's that geometry here of our bunny here. Now, that's going to be our driving problem, detecting collision, but let's just go ahead and take a look at this bunny for another moment here. And what you're seeing here above me is a wireframe of this white bunny model. That means the actual lines that are being shown are overlaid on top of the object here that you would see here. Okay, so that's what I mean by the wireframe here. Now this is called, when I'm thinking about the geometry, the actual mesh, or 3D mesh in this case, because we have 3 dimensions. So again, just orienting you to the 3D terminology here. And that's what represents the geometry here. Okay, so if you go ahead and take a little bit of a closer look here, I've highlighted a few of the points here, which we call vertices or vertex, and the connection between them, the line segment, that's called an edge. Okay, that's representing some relationship between these vertices. 2 vertices that are connected make up a line segment or an edge between them. Okay, and that's the actual geometry. Now, when I talk about this and we think about things in geometry, this very naturally looks like something that we would just represent as a graph. And I've kind of represented that in the mathematical notation here, where I say a graph G is made up of some amount of vertices and some amount of edges. Okay, so that's the sort of notation that you're going to see in these sort of geometry problems, or for those of you who have done some graph theory or discrete math, where you might have learned some of these terms here. Okay, but again, even though this is a 3D object, again, as a computer scientist, we often like to take these types of problems and translate them into some graph problem, something that we know how to solve there. Okay, so that's going to help us with the representation. And again, the representation of geometry and the different types of data structures, those are other things that we would want to think about in a introduction to computational geometry course here. Okay, so there are some other key observations to make with this particular 3D mesh. One of them being that this is actually made up of triangles. So, let's kind of explore this just a little bit more here. What we have here, this idea of polygons and triangles. All right, so as you might expect, we're going to be working with polygons on this field of computational geometry. So here are some example polygons, regular polygons, irregular ones, triangles, which happen to be particularly important in computer graphics for a multitude of reasons. We can have concave ones, irregular ones, etc., etc. And I found this nice chart. Here's the sources down here, highlighting again the different classifications of polygons, right? Sometimes we think about them when you learn about polygons right above me on this column as, the number of sides that we have to this actual shape, 3, 4, 5, 6, etc. And then also based on the relation between these sides and the angles. So this is taking you back to your geometry class here. But I want to just focus on two types today here. Right above me here, first listed convex polygons, and right below concave polygons. Okay, so let's just go ahead and have a reminder of what those exactly are. So again, this is probably taking you back to your geometry days. And well, definition of a concave polygon, if I take your attention right over here, is that a concave polygon is a polygon that's not convex. Okay, that sort of makes sense. So what's a convex polygon? So let's go ahead and see what that is here. Well, just below the definition, right, a simple polygon is concave if and only if at least one of its internal angles is greater than 180 degrees, right? So if we take a look at this angle here, right, this sort of angle here is going to be greater than 180 degrees. And by internal angle, well, that means that we need to, pick one of these angles here, which I highlighted. So let me just be clear that it's right here. This angle here is formed is greater than 180 degrees, right? And that's a obtuse angle, right? So that's the idea. So for our convex polygons, right, we can't have anything greater than 180 degrees here, right? The opposite here of concave. Okay, so that's our sort of definition. Intuitively, we usually know this by looking at it. Something that is convex is kind of this, more compressed looking shape, where concave has, something wide open, a gap here. Okay. Okay. Now, when it comes to this, and again, I think maybe folks understand this definition here, in computer graphics, we tend to prefer these convex versus concave polygons for a multitude of reasons. And we're going to talk about, or I'll mention triangles a little bit here. There's actually many reasons why we like triangles when it comes to actually doing computer graphics, but today, we're going to observe some other types of properties here. So again, just to give another definition of convex polygon to make it concrete, this idea of convexity, we say a shape or a set is convex if for any 2 points A and B in that set, the line segment forming AB, this is the line segment, lies entirely within this set here. Okay, so essentially that's saying, hey, if I can draw here for any 2 points, maybe they land on a vertex here, everything in that line segment actually lands in this actual shape here. Right? If I go back a slide here, you can see where if I pick this point here and then another point down here in my non-convex shape, and I connect that line segment, right? I've got points here on that line segment that are outside of the actual shape, outside of that boundary here. Okay, so that's just another way to think of the convexity. And again, as a mathematician, we might think about things that, these points that we pick don't exactly have to lie on a vertex. So here's just another rendering of that here. Okay, so one thing that we like to do with our geometry as computational geometers is to actually triangulate our polygons. Now, again, we like to work with triangles in computer graphics. I don't have a slide dedicated to this, but because a triangle is actually planar, right? It doesn't fold in any way. You can't twist it. If you sort of move one of the vertices in any dimension, the actual triangle stays flat. Okay, I'll take an example here. I have a piece of paper here. This is a quad, but if I pull one of these edges, see how it sort of bends here, and then I get sort of this round curvature. That tends to be actually kind of hard computationally. It takes more computation to actually draw this shape here, especially for real-time graphics. Now, if you're doing animation or working on a Pixar film or something, you might actually prefer to have quadrilaterals as your primitive, a four-sided shape. But triangles are nice. They're flat, so we can figure out exactly what is showing here. So often what we'll do, this is a long way of saying, if we have this convex polygon, like this one up here, is we want to break it down into triangles. And we can do this relatively trivially, right? So for this actual polygon here, I can actually sort of draw this fan by just picking one vertex and connecting with all the other non-neighbors, right? So I can't pick what's right next to it because they're already connected, but these non-neighbors, and that will make triangles here. So I have 1, 2, 3, 4 triangles here, okay? And again, it's important as we go through this introduction to computational geometry to realize that we can have many different triangulations, right? I could have picked a different edge and ran that same algorithm and gotten something unique. I could have, drawn one from here and then sort of crisscrossed in different directions. That would have given me different triangles. And picking those triangulations and good ones or different ways to triangulate various polygons is actually important to think about. And again, that's something that we might cover more in depth in a geometry course here. But let me go ahead and show you what happens with our concave polygons, right? If I just sort of pick a vertex here, and if I try to connect it here to some non-neighbor, well, that would fail, right? And we would have to do some sort of test to figure out, hey, not all the points fall in the actual polygon, so that's an illegal part of the triangulation, so pick some other edge. So it's not that we can't triangulate a concave polygon, it's just that it takes more work here, okay, to get our original triangles here, right? This is trivial, and then we can come up with many other triangulations much easier here. All right, so this sort of idea is, decomposing our polygon into triangles, just decomposition here. That's the idea and part of, again, something that you might do in computational geometry. Okay, so that's something that you can take a look at here. So again, these are just my notes here stating that there is not one unique triangulation for an object. Again, you can sort of do this example and you can actually see how many that you could come up with and probably prove how many different triangulations that you can actually have for some object with some amount of polygons here. So there are some other nice, YouTube videos I'm going to link here that you can check out, and then the wiki page on Polygon Triangulations. I can actually just click on it here, just so you can kind of think about this shape here and how many you can get here. There's often things that you can sort of think about, like coloring and where these sort of edge cases are interesting. And this picture is actually pretty interesting for the case that we just talked about. I'm going to click on it just to show you the different types of triangulations that you can have. Okay, so something to take a look at if you look at the Wikipedia page there to start, and then a little YouTube video if you want more help here. All right, so back to our original problem here, we're at least more convinced maybe that, okay, working with this bunny that's made out of triangles, the triangles are important because at the very least, triangles are a convex shape here, okay? The interior angles are smaller than 180 degrees. And then there's also this idea about a triangle being a planar surface. And then again, with the surface being planar, we get some other nice properties with, the normal being easy to compute and so on. But again, let's just go back to our original problem here and just see if we have, what happens when two bunnies collide. And you can kind of, just to help you parse this picture, draw your attention towards where this collision's happening here. This image happens to be transparent, so you can actually see the bunny sort of intersecting here. Okay, and I want to know programmatically, how would I detect that this actually happens? How would I know these two bunnies collided? So, the assumption is, again, that this mesh is made up of a bunch of convex shapes here, triangles, and it has been perfectly triangulated, as you can sort of observe here. How would you go about doing this? So, go ahead and pause the video for a moment and try to think about what your strategy would be. And, hopefully it took a minute to pause the video and think about what you could do. But I mean, let's just start with something sort of naive here, right? We could sort of do an intersection test between every single triangle, right? I could sort of look at the bunny's nose and say, hey, did it collide with this bunny's nose, right? So we'd have sort of a triangle to triangle intersection test, where we treat, which is really just saying, hey, did two planes intersect? Okay. So we'd sort of test that first, and then we'd say, okay, do these points of intersection within the plane, meaning in a triangle, actually intersect? And we'd have to think about that. And then we'd move on to the next triangle. And we say, okay, for this nose, now check, this part, then this nose, the right ear, this, part of the nose, the left ear, etc., etc. Okay. Now that's looking like a pretty expensive algorithm to test every single triangle against these other triangles here. So how can we solve intersection in a reasonable way here? Okay, well, again, we have these sort of triangle to triangle intersection tests. And again, if I'm checking every triangle to every triangle, that at least is looking like some sort of nested loop here. Okay, so some sort of n-squared algorithm, and then whatever the cost is of our actual intersection test for triangle to triangle here. Okay. Okay, so let's kind of think about this a little bit here, how we could go about this. What we do have here, which is kind of nice, is this tool for doing intersection here. Now, what we could actually do here is we could sort of say, hey, let's take, our actual triangles that make up this mesh, okay? And we also have this property, I haven't defined this term, a convex polyhedra. So, what makes this a convex polyhedra, this bunny? Well, it's made up of convex shapes, and the normals don't fold sort of inwards, right? There's no like cave inside of this bunny here. So this is a convex polyhedra. And what we're going to go ahead and do is sort of say, hey, let's take, one of these triangles, again, sort of pick the bunny's nose here, and we want to project that position. So we have a tool for this in linear algebra, projection, onto a line here. And we sort of do this in the x, y, and the z axis. And if there's overlap in all three, the x, y, and z axis, there must be some sort of collision. Okay, so we sort of do this test, and this is what we're essentially doing when we're doing some triangle to triangle intersection, just projecting all of our points onto line and testing to see, is there overlap amongst those triangles, okay? So this sounds like, a relatively expensive test, but, it's kind of a neat trick here that we have this sort of what's called the separating axis theorem, SAT, this sort of test here that we can actually do here. Now, again, think about how expensive this might be if you're taking each of your convex shapes, and maybe I should have drawn triangles here because that's what we're doing, and projecting where they fall on the x, y, and z axis. Okay, so this is a tool that we can use here. Okay, so observe though how this test actually doesn't work very well if we have a concave polygon and a convex polygon, because when we do this projection, right, of the actual triangle onto the line here, well, we could have something like this that falsely produces a collision here, because when we project, this point over here, which I'm sort of highlighting on the left here, down with this point, right, it fills in this gap, but there's no true intersection. Okay, so again, the concave polygon that we're working with is a little bit trickier for us to actually use. We would actually have to do some triangle, test here amongst each triangle. All right. So this is, again, where we can use some tool here like projection, or linear algebra tool here, to figure this out. Okay. Okay. Now, again, this is my note that we're applying SAT on each of our x, y, and z axes. I've got one drawn here. And you can get sort of early termination too, as soon as you say, hey, there's not an intersection on one axis, right? You could imagine the bunny sitting perfectly on top of the other bunny in some way here. So if it's on top, then, well, it's going to intersect maybe in two of the axes, but not on the y dimension, right, where we're projecting onto. All right, so this type of detection itself is very precise, right? We're sort of doing this for every polygon to see if there's some sort of collision. And we could kind of figure out exactly which polygons are actually colliding, which is kind of cool. But again, you know, this bunny here, 69,451 triangles. And if I have two of them, and they're moving and constantly, you know, reorienting, this is a pretty expensive test that we have to perform here. So my question to you, you know, thinking about some geometry is, could we approximate this collision with two bunnies in a simpler way? I'll go ahead and give you a moment to think about that. And hopefully you paused the video and thought about this for a moment, but how else could we, you know, approximate collision with bunnies? Well, let's use simpler shapes. Okay, let's approximate the shape of a bunny with something else here. Okay, so the simplest approximation that we can usually come up with is a sphere. Let's put this bunny in a sphere, which I've represented with a circle here, and we call this a bounding volume. Okay, so now I can use this simpler sphere here where I know the radius and I know the center of this sphere, and then I can just sort of determine, hey, if the distance from the center of one of these spheres is less than the sum of both these radius, then there must be some intersection, right? Because at most, if I sort of, again, you can do this experiment if you have two bouncy balls or something, pick the center point, estimate what the actual radius is, or measure it exactly with a ruler, and see if that distance is greater than the center of the sphere, then you have a collision. Okay. Now, what's the problem with this bounding volume? Well, you could imagine how we could have some false positives, right? Look at all this space here that we have, okay? Where we could have this empty space, you know, if this bunny is intersecting in part of the sphere, but not totally here. And I could go ahead and just modify this example to show you here. Let me go ahead and just highlight these two here, right? If I sort of move this just a little bit here, right, we can clearly see they're not overlapping the actual geometry, but the sphere actually is. So we get sort of a false positive here, okay? Now that might be okay, and you might use this maybe as a first check to see if it's worth doing that more expensive triangle test. And that's what, in fact, tools like ray tracers and stuff will do. But again, this is one of our tools that we can use here. This idea, at least, of approximating this shape with a simpler volume. Okay, now we can use boxes. Maybe that more accurately captures the bunny. If we start using boxes, then we might even think about the orientation of the box, right? If the bunny sort of spins, then we reorient the box, and that has a name, oriented bounding box, versus just something that's axis aligned and sort of fixed. We might use capsules. So again, folks coming from maybe a game programming background, game engines like Unity 3D and Unreal often have capsule colliders, where again, you could approximate, you know, part of the shape in a box and then the ends with a sphere or hemisphere on each side. So those are just some techniques that we could use for our bounding box, okay? So again, you know, go ahead and, I gave some of the trade-offs, but go ahead and pause the video and see if you can list what some of the trade-offs are. All right, and hopefully you paused the video for a moment there and thought about just, again, what some of the trade-offs are. You know, this is a precision versus speed type of thing here. You know, a sphere approximating a bunny, which is not a very spherical shape. It's going to work fast, but again, you might get some of these sort of false positives saying that there was actually a collision when there wasn't. Okay, or if you're using this sphere to sort of model how the bunny moves, you can imagine a bunny rolling down a hill in a sort of spherical way. It's just not as nice here. Okay. So what could we actually do to better approximate the shape of the bunny and get more improved collision? Well, there's sort of a happy in between here that we can do, and that's generating something known as a convex hull. Okay, so let's go ahead and talk about what a convex hull is. And the idea is a convex hull is the smallest convex set that contains all the vertices. Okay, so we defined what convexity is, right? Being able to draw a line segment from one point to the other, and it falls inside that shape. But we can sort of observe here with this example that I have of this dragon here, another famous 3D model, the convex hull, where you can see that it is tightly sort of packed here. Or tightly wrapped, and we'll come back to that term of wrapping. And the dragon is completely encapsulated here. Now, again, contrast this with something like a sphere, which might have more sort of empty volume. So again, we can see that this is a better approximation. And if you look closely on the video, depending on your resolution, right, you'll see the actual triangles here and this red sort of mesh here that make up the convex hull, the surrounding shape to the dragon. And then you can go ahead and, again, hopefully infer that, there's many fewer triangles here in this convex hull shape than the actual number of triangles that we would need for this dragon. It's got the individual points here, but again, this model has several thousand polygons versus what might be maybe 100 triangles total for this convex hull. Okay, so how do we actually get this algorithm here? I've given you a little bit of a hint here of, if I just have a random set of points here, a bunch of vertices, how I would actually generate this convex hull. So you'll see this, this is from the Wikipedia animation here, generating somehow a set of edges here that surround all the other points. So they're all included in this final hull that is generated. So I'll let you go ahead and think about that. And if you thought about that a little bit, again, the analogy, just sort of a hint here, that's sort of the classic example that's given, is if you have a bunch of thumbtacks on a board and you put a rubber band around them, the rubber band's going to snap around those thumbtacks and form the actual convex hull. Okay, you can actually do this experiment again at home. Just be careful with the thumbtacks and the rubber band. But the actual answer for the algorithm, this is what's known as a gift wrapping algorithm. Okay, and there's many different variations of this. I'm going to give you an example today in our introduction, and this could be something that you could go on to code up, right? You just plot a bunch of points here and maybe do the gift wrapping. But a sort of classic one that is given is what's known as the Jarvis March, again, early in the 70s, right? As computational geometry was getting a little bit more formalized. And again, the way this sort of works, I just want to give you the intuition, is if I just pick, some points here, we're trying to find the next point such that when I select this point, I'm sort of doing this test, that all the other points fall on the right side of it, right? So we can kind of clearly see that. And by definition, we probably want to start with a point that's maybe the furthest on the left, or some case. And you might have some edge cases, right, where you have 2 points that fall, they're collinear, right? They fall on the same axis here and are equal. Just pick one of those, okay? So let's pick this point, P0 here. And then what I'm going to go ahead and do is search for this point here, right, by testing the other points. And I see that everything's to the right of this, okay? And then, if I take this point and I test this point, and you got to kind of turn your head a little bit here, but if you turn and sort of align yourself with this line segment here, you'll see that everything falls to the right of it. And then if I pick this point and then I've got to turn my head all the way around, so don't, hurt yourself doing that, then you'll see that all these points would be to the right of this line segment. So if you keep repeating that process, and that works, you get an algorithm that runs this in what we say O of n of h time here for the Jarvis March, okay? So try to convince yourself that this actually works here. And then in practice, if you want, you can look at a variety of the different gift wrapping algorithms. Okay, so this is Jarvis March, which is gift wrapping. Most folks, I think, in a course, you would also want to look at gram scan. That's another one that gets you n log n. Quick hull would be another one. And then you even see that some of these, we start even getting better and better with the different algorithms here. Okay. So, those are just some different things to look at here. Okay. For generating our convex hull. Okay, so now that I've got this convex hull here and I'm comparing it on the right side versus the box, again, see that it's more tightly approximated, right? The bounds are here. That's by definition, that's what the convex hull is here, okay? And it's again simpler. I would say this is maybe 100 triangles at most here versus the 40, however, 65,000 or whatever triangles that we had, the many thousands of triangles that we had in this bunny here. So, less gaps here, smaller volume here, better approximation of the shape. And again, we can use this convex hull for collision detection, which we'll revisit, which was sort of the point of this talk here, but as well as in a physics simulation, if, we have this convex hull that we're using to model forces, right, we can actually compute a more accurate center of gravity, right? Where are there more triangles here? These types of things that we would want in a system. Okay, so now our collision of the two bunnies, again, we can do this same SAT test here, again, with each of our triangles, but again, this time we're just using, I don't know, 100 or so of the triangles here to do this approximation. Even if we're trying to do something like just saying, hey, let's iterate through each of these triangles and do a triangle to triangle test, we're still doing fewer things. And again, this might be more important, say, for depending on the type of application you're building. I could imagine a video game with more hand-to-hand combat that you would want to use, again, a convex hull versus a sphere, or in some cases, maybe you would still subdivide your object, like this bunny, like the head, you'd have a convex hull, and then the body would also have its own separate convex hull, right? So you could sort of partition this actual geometry and get an even tighter bounds and have two convex hulls, etc., etc. So this is just a tool that we've learned here that we can use to get better approximations. Now I'll get out here so you can see the full image. All right. And let's go ahead and wrap things up here for this talk here, because it's gone on quite long enough. But the idea is that we've looked at some fundamental primitives. Hopefully just giving you this introduction to computational geometry is something that you can be excited about, know some of the algorithms, where to search next, and to understand the importance of some of the primitives that we would use, convex polygons, specifically triangles, to solve problems, and why it's important to actually go back to that math that you learned maybe in high school or middle school, depending on whenever you learned it earlier in your life, and how you can actually apply it to solve some of the problems, and why we paid such attention to formalizing certain properties of these objects. They end up being useful when it comes to computation. So I think that's a very exciting thing about computational geometry itself. All right, so, just to give you some more ideas of things to explore that might actually be fun. Again, this is an issue that, or sort of a topic that I care about, things like mesh data structure, mesh representation, right? Maybe just a list of vertices, an edge list. And there's different types of data structures, winged edge, half edge, etc., that are interesting because we can modify them. Okay, so you could kind of think about those data structures. We probably want to look at more algorithms related to triangulation, right? Because sometimes we don't always have a mesh that's been triangulated. So there's interesting things to do there. Not directly related to computational geometry, but numerical precision is something that we want to also think about, just in terms of, again, knowing how to work with some things like floating point values and such. Again, different algorithms for triangulation, again, sort of this idea of decomposing polygons into different shapes. There's also interesting, or things that you might want to do, transformations like finding the dual of a mesh, which is sort of flipping the vertices with a number of faces here. So different things that you might want to look at. Constructive solid geometry, that's what this example of this picture is. So using Boolean algebra to compose shapes. So if I take a box, for instance, and union it with this circle, I get this sort of shape. And on the right side, if I, starting from the bottom of the tree, take these cylinders and union them together, I get this sort of, shape here. And then I union that with yet another shape here. And then I'm actually subtracting from our previous sphere box this shape, and that's how I get the holes in it. Okay, so this is how we can do modeling, and oftentimes you'll see this in like a CAD tool or something. All right, then as I mentioned before, motion planning, is used in robotics. This could be things like shortest path. Oftentimes it's things like shortest path if I've got like a robotic arm that has constraints, so it can only rotate in certain angles. So can I sort of pick up an object? How do I minimize my energy for this sort of shortest path? Again, if you've got a robotic arm on an assembly line, but, with the constraints of, what the degrees of freedom are, what axes it can turn on, these types of things, also very interesting. All right, and just to give you a few fun things, I want to give a shout out to this channel. This had a very fun video on more computational geometry problems that had related to do with triangulating objects and stuff. There's sort of the art gallery theorem. This is probably the first problem that you learn about. It's usually in the introduction of geometry textbooks that I think is really fun. And Zach Sadar's channel here made this video, a visibility problem, how many guards are enough? And I think this was really cool visualization of this actual video. So just want to give a shout out there. I'll get out of the way so you can see the whole thing here. And I captured a little animation here we can see the idea of sort of placing guards in video games and how this could actually be kind of applied here. It's a fun problem to think about. All right, resources as far as books. Here's 2 books that are pretty good, sort of the standard, the Marx book here, Mark DeBerg, Mark, and so on, the 4 authors here. Here, I'll just click on the page here so you can take a look. Computational Geometry, Mark DeBerg, Offred Chung, and Mark Van Kreeft, and Mark Overmars. These authors here, this is a nice book that I was given in grad school that, you know, it's just sort of told you could just curl up and sort of read this book because it's very readable and a fun book to take a look at. So I still have my copy. As well, I have this other copy here, Computational Geometry in C, that has actually some code for these algorithms. So, you know, you can actually take a look at. And that's been a book that's been around for quite a while and it's quite nice to use. All right, so with that said, folks, thank you for watching this talk. Again, this was a recap of a talk I've given at university, and I hope you enjoyed it. I hope it serves as a nice introduction to computational geometry. It gets you excited about the field, and again, if you're learning computer graphics or something, this might be something that you want to dive into further. All right, with that said, folks, make sure if you enjoyed this that you go ahead and give it a big thumbs up. Subscribe if you want to see other types of videos related to all the things on my channel. Check out the courses if you're interested in applied sort of learning, and otherwise comment below. You know, do you want to see more videos like this? Do you want to see more geometry? This is something I'm clearly excited about and going to be exploring, but perhaps in the future could be something we see more videos, but you have to let me know. So with that said, folks, thanks for your time, and I'll look forward to seeing you soon.